very happy to have Jean-Luc give us our first remote Zoom talk in the fluid seminar on homogenization and why shape matters. So, okay, thank you.
Thank you, Theo, and congratulations on the new baby. I'm sure it's a great time to have a baby right now. So this is joint work with my graduate student Hongfei Chen in Madison, and we've been interested in looking at models of Brownian microswimmers. So what I mean by a Brownian microswimmer is a kind of old model for this, which is very natural. So if you have a swimmer and a microswimmer, I'm assuming everybody knows what a bacterium or a spermatozoa or something like that, some microscopic organism. You often model them as balls or ellipses or things like that. I'm going to be strictly two-dimensional for the purposes of this talk. But the model is the following. The swimmer likes to move at a fixed velocity in the x direction in its own frame. In other words, there's an axis of swimming for the swimmer, and there's a perpendicular direction, again, in its own frame, and there's an angle that it makes with the horizontal, some absolute horizontal, and then this satisfies a stochastic differential equation. The position of the swimmer satisfies a stochastic differential equation. dx is u dt plus square root 2dx, that's the standard normalization for diffusivity, times a Brownian motion dw1, an increment of Brownian motion. And similarly dy, the y displacement, is the same except it doesn't have a velocity. So the y displacement only has an independent noise, right, with diffusivity y. And then finally, what makes the model interesting, so far this is just swimming plus position plus a little bit of noise. What makes the model interesting is that you also add a rotational diffusion. In other words, there's a third Brownian motion that you add to this, and the angle is Brownian, so this swimmer likes to move around and just is always kind of turning its orientation as it swims. Okay, so that's the general model, but you don't actually solve it in these coordinates because these are the coordinates in the sort of the frame of the swimmer. So instead you rotate it to the so-called the laboratory or the fixed frame. So in the fixed frame, that means I'm going to rotate everything such that I'm going to use axes little x and little y, which are fixed in space as opposed to being rotated and moving with the swimmer, in which case the stochastic differential equation becomes three equations for these little x and little y variables, which is u dt plus the square root of 2dx dw1 times cosine of theta. In other words, there's a rotation by cos theta that mixes these two equations, and then another one, normalization is such that the counterclockwise rotation, root 2 dy sine theta. Okay, so it's just a rotation, and again you get a similar equation for y, which would be u dt. There's no u in this case. There's just root dy. Yeah, there's a u dt plus root 2dx dw1 sine theta plus cosine of theta root 2 dy. Oh, I put the sine theta twice. I meant to write dw2. Okay, so again, when I rotate the system, I start mixing these different components together, but the theta component stays the same. In other words, the rotation in the angle doesn't care if I have an overall fixed rotation on this, it doesn't change the equation. Okay. So this is useful, and we sometimes it's convenient to use this particular form, but most of the time we actually want to study the Fokker-Planck equation associated with this. So Fokker-Planck, also known as the Kolmogorov-Forward equation, which is a PDE for the probability density of swimmers. So it's a PDE for a quantity py theta t, right? So it tells you the probability of finding the swimmer at position xy and angle theta at time t. And this PDE just looks like dp dt plus div of a drift u times p minus a diffusion tensor grad p is equal to 0. Okay, and then I need to tell you what the drift is. The drift is u cos theta, u sine theta 0. So there's no drift in the theta direction, though there could actually be drift. In some models, you actually put a net rotation on the swimmer, a kind of time-dependent, a kind of fixed rotation, which is meant to model the fact that some swimmers actually tend to go in circles, right? Alex, did you have a question, or you just accidentally turned on your camera? Okay. And then the diffusion tensor. This is a very anisotropic process, at least the way it's formulated. The diffusion tensor is a matrix that looks like dx. I think it's cos squared theta plus dy sine squared theta, then a half dx minus dy sine 2 theta, and then 0. This is reproduced. This looks like a similar thing, dx sine squared plus dot 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 0 1 d theta 0 0. Sorry, this is falling off the board a little bit, but it's not terribly important. It's just saying that there's a diffusion tensor, and in the, a natural limit is to assume that the diffusivity in the swimming direction is the same as perpendicular to the swimming direction. So if you make the assumption that dx is equal to dy, then this tensor actually becomes diagonal. So you just get that this is dx dy d theta. Okay. Everything fairly clear about the model so far? So again,
the dx, dy are numbers. They're just,
yes, that's right.
they're diffused.
D capital X and D capital Y are just numbers, but I will often refer to the entries of D itself as dxx, dxy, dxy, dyy, d theta. And these four, the spatial diffusivities are functions of theta, but not of xy. Okay, so they can be function of the orientation, but they're not functions of position. Though the theory would, you could allow them to be if you want to, but in this model, I'm not allowing them to be. Okay. So even this very simple equation has been studied by some people. In particular, there's a recent paper by Kurtz-Haller and what's the name again? Franoche in 2017. Where they find the Green's function for this equation, it's actually what they call, it's the scattering function. So it's actually the Fourier transform, the integrated Green's function Fourier transforms. It's something that's used in optics, basically, because you're interested in how these little swimmers kind of head towards an obstacle, say, or if you imagine that you have a release of such swimmers, you want to know how they spread out. And they'll spread out anisotropically because of the swimming and because of the dx and dy. So even in this form, this is fairly complicated to solve, and you can almost write down closed form solutions in terms of Mathieu functions, but they're not terribly useful because they're so complicated. Okay, so that's the basic model that I want to present. Any questions before I flip over to the next blackboard or whiteboard? Look at this. The problem is that you do need to erase eventually, right? You can't get away with it forever. Okay. So that's what as I said, that's what I call the basic model. But so far, there's no boundaries. So there's no boundaries in the sense that the swimmer doesn't encounter, I haven't said anything about the domain in some sense. I was discussing this as if it was a release of this swimmer in space, but in general, we might be interested to see how this swimmer interacts with boundaries. And what's interesting about this is that the shape of the swimmer will now start to matter, in the sense that the exact detailed configuration of the swimmer will actually start to matter in a way that becomes very interesting. So how are we going to model that? Well, we're going to look at what happens when a swimmer first comes next to one wall. So consider a boundary. This is a wall. And let's say the swimmer approaches this wall. So the swimmer comes near the wall, and let's say the swimmer just touches the wall barely, right? So the swimmer has an angle, a swimming angle theta here, and it just happens to just be barely touching the wall. So what I want to first describe is the so-called configuration space of this swimmer. In other words, there are 3 coordinates, and in theory, you know, the center of rotation of the swimmer can adopt all 3 coordinates independently, but some of these pairs of coordinates will correspond to entering the wall. So you have to start asking which are the allowable values of x, y, and theta, and you can express this in terms of a function, which we write y star of theta. And y star of theta is, we call it the wall distance function. What it is it's the distant, the minimum distance to a plane wall, given that the swimmer has a fixed orientation theta. So in fact, it's actually closely related to the convex hull of the swimmer, because first of all, the swimmer appears as a convex body when you approach the wall, because if it has any concave bits, they don't see the wall, right? If I have a plane wall, then the swimmer might as well be a convex body. So then this function y star is what you get by rolling the swimmer along the boundary and watching how the center moves. In particular, for instance, for an ellipse, you can show that this y star of theta is the square root of a squared sine squared theta plus b squared cos squared theta. So for an ellipse of semi-major radius a and semi-minor radius b, this is the formula. I'm always going to assume, by the way, that a is bigger than b in what we're doing here. I'll comment at some point about what happens when a is less than b. It's actually interesting because it'll lead to different dynamics. So it's actually kind of a different problem to consider a less than b. The dynamics of the swimmer are quite different. Okay, let me just plot this for you, just for a sort of a reference. What does this look like? So this is, the domain is in theta is minus pi to pi, and I'm going to plot this y star function here. Let me use a little bit of colored pens, might as well, since we have them. So the wall distance function is this function. So there's a point of closest approach. The function looks something like this, and this part of the domain is inaccessible. The swimmer is only allowed to be above this function y star of theta. So we're going to call this part of the domain omega, and this is going to be the boundary of omega. So in general, omega will always be the accessible position of the swimmer, so the configuration space, and d omega will be the boundary of that space. One thing that's important to keep in mind is that remember that the drift function that we had earlier, our drift function was u cos theta, u sine theta, and 0. So the velocity of the swimmer in x, y, theta space is this function. And if I superimpose this here, this corresponds to a downward drift here. Sorry, I'm drawing over my pictures, which is not very good practice. But the point is that the y velocity of the swimmer is u sine theta, and here the vertical axis is y, so I can see that the swimmer on this left side is moving down towards the boundary, and on the right side it's moving up. And so if I consider a trajectory, a stochastic trajectory, just as an example, a typical swimmer will be doing Brownian motion here. It will hit the wall, but then I'll put a boundary condition that I have to preserve probability. There's no probability flux through the wall, and so the Brownian particle will move over here, But then on the right side, it gets grabbed by the upward drift, and it tends to wander off. This is what I would call a scattering event, meaning it corresponds, let me draw the true picture, the physical picture of what's happening. When the swimmer is going this way, it's approaching the wall. And then when it crosses theta equals 0 here, that's when it becomes horizontal with respect to the wall. So it curves. And then finally, it manages to exit the wall region, and it leaves. So the very pleasant thing about modeling the stochastic process and including the shape of the swimmer in our configuration space is that already we're seeing the kind of, if you just run Brownian trajectories in this model, you see that they do something very similar to what's observed in experiments that the swimmers actually do. Swimmers do tend to spend some time aligned with the wall and then eventually kind of leave the wall. And in this context, it's all arising because of the Brownian fluctuations, that the swimmer has these kind of sleeping modes where it gets trapped near the wall, but then eventually there's a big enough fluctuation that it manages to leave the wall area. Okay. So again, this is approaching the wall, so that's the left side of my domain, and this is leaving the wall, so that's the right side of my domain. Okay. All right. Questions so far? So let me remind you that the PDE that we're solving then is dp dt plus div of up minus d grad p is 0. So that's the equation we had on the previous slide. I'm not going to write again what u and p are and d are, but they're just, well, this is u actually. D is some big matrix, but you can think of it as a diagonal matrix if you want. And then the question is, what boundary conditions do I put here? Well, this is a probability flux. Right? This is the conserved probability flux from this conservation law. And so the natural boundary condition is to say that the normal product, the normal component of the flux vanishes at the boundary of my configuration space. That's the natural boundary condition, and it also gives you automatically this nice kind of scattering behavior of the microswimmer. Okay? Right. So that's for one wall, and there's a lot of interesting things you can say even about one wall. Hongfei and I have a calculation where we show the kind of distribution of angles that swimmers can have as they exit the wall, and these turn out to be similar to what's being suggested in experiments, and people have actually much more complicated models to explain this, and we kind of think that it can be explained with this very simple Brownian model. But that's not what I'm going to talk about today. What I would like to do is to add a second wall now, to have what we call a channel configuration. So everybody understands what I mean by a channel. What I mean is that there's a pair of parallel infinite walls, and my swimmer is somewhere between the two walls. The two walls will be separated by a distance capital L. Okay. And so now if you think about this is basically reproducing this picture of the parallel wall twice, right? In the sense that there's going to be one of these functions y star corresponding to the bottom wall, and a flipped over function y star corresponding to the top wall. So the configuration space will look something like this. So let me draw a similar picture to over there. I have my y-axis again. And this is going from minus pi to pi again. And at the bottom wall, I would just reproduce my picture from over there. So the bottom wall just looks like this. And the top wall, you take this curve and you flip it over. Of course, this particular curve is symmetric, so flipping it over doesn't change very much, but I'll still plot it. It looks something like this. And again, now the excluded area, the region where the swimmer is not allowed, is all of this region here. Okay? But my little swimmer, and again, the swimmer is now represented by a single point in this configuration space. The little swimmer is now undergoing its motion, Whenever it's in negative values of theta, there's a drift downwards, and whenever it's on the right side, it's got a drift upwards, right? So it looks its little trajectories will look something like this. It'll again be scattering, but this time it can hit both walls, and it can get trapped in certain ways. The boundary conditions are periodic in the theta direction, of course. Okay. Again, I'm going to call the interior of this domain omega, and I'm again going to call this boundary d omega. Let me just see that I didn't forget to say anything. Let me just say that the shape of these two curves, the bottom curve, so this is what we'll call zeta plus of theta, and this is zeta minus of theta, and they are just related to y star, in the sense that zeta minus of theta is y star of theta minus L over 2, and zeta plus of theta is minus y star of theta plus pi plus L over 2. Which the second one is just a kind of rotation by pi of the bottom wall. There's a special case which we'll actually be using, the ellipse already satisfies it, but there's a very important special case which is a swimmer that has an axis of symmetry along its swimming direction. So I call this a left-right symmetric swimmer. So if a swimmer has so-called LR symmetry, then it satisfies that y star of theta is y star of pi minus theta. In other words, this wall distance function, if you're approaching the wall this way, it's exactly the same as approaching the top wall this way, for instance. Or, sorry, if you approach the wall this way, it's exactly the same wall distance function as approaching it pi minus that angle, because the swimmer is left-right symmetric. But actually we'll see that this can be important because you get different types of dynamics depending on whether the swimmer has this axis of symmetry or doesn't. And for biological organisms, usually a biological organism is left-right symmetric, except that it's never quite left-right symmetric. Biological organisms have lots of imperfections and broken symmetries, and so having a little bit of breaking of the left-right symmetry is actually quite important in biological applications. Okay. I should also say, by the way, that this shape, this function y star, is actually related to the Legendre transformation of the shape of the swimmer. Because if you think about it, when you take a Legendre transform, you're transforming from a variable to its tangent space. And this is basically what you're doing by looking at the planes that can touch with the wall. So there's some nice convex analysis that could be done to maybe show things in general. And in fact, interesting challenge is to try to do these sorts of things in 3 dimensions, where the plane of contact, the shape of this space, is a much more complicated object. We haven't really looked at this very much, but it's clearly a much richer problem in 3 dimensions than it is in 2 dimensions. In 3 dimensions, if you do an axially symmetric body, then it's very similar to a 2D problem. But a general 3D body can have a very complicated configuration space. Okay. Still no questions? You guys are very quiet. It's just hard to see if anything's happening. Who knows? Maybe I lost the internet connection 5 minutes ago, right? Okay. So, I'm going to erase this. Okay, so what I would like to do now is to actually solve the Fokker-Planck equation in this channel. So, I forgot to erase the part. So let's look at this Fokker-Planck equation in the channel. So again, let me remind you what the equation is. It's dp dt plus div of up minus tensor grad p equals 0, and we're applying our boundary condition that f dot n is equal to 0 on the boundary. Okay. So, and let me point out that in the channel geometry, we can often learn a lot by just assuming that p is a function of y only. So in other words, we're going to look for solutions that are not a function of x. So we're going to look for translationally invariant solutions. Either that, or either you can look at X average solution. Both of them lead to the same kind of equation. So, but this simplifies the problem because, of course, now we have a two-dimensional problem plus time instead of a three-dimensional problem. Okay. So, in general, of course, this is a very difficult equation to solve, in particular because of the boundary conditions, right? These no-flux boundary conditions at the boundaries are quite difficult to deal with, to get analytical solutions. Numerically, of course, and even with some analytical techniques, there's no problem. But as far as getting exact solutions, this is a bit of a problem. So let's try a simpler limit first. So a simple limit is to take the rotational diffusivity, d theta, to be small. It turns out that this is actually quite a nice limit because if you set d theta to 0 in the equation, you can actually solve the y problem exactly. Okay. Oh, and you also have to rescale time to make sure that your time dependence actually happens on a faster scale than the d theta time scale. Sorry, than the dy time scale. So from this, we use an asymptotic expansion. We write that P is P0 plus epsilon P1 plus dot dot dot, the usual sort of asymptotic expansions in powers of epsilon. And I'm going to spare you the details of how this goes. It's fairly standard, but you get a nice answer out of it. You get a solution for P0 of y theta t, which is equal to, and I'm going to tell you what big T is in a second. I'm going to define big T to be d theta times little t. So it's a bit of a dimensionless time rescaled by the diffusion constant. So I can rewrite this, again in this expansion, as a function of theta and t times an exponential of sigma theta y. So, you know, the y dependence, in other words, separates because you solve for it at leading order. And then you have to find an equation for capital P by going to higher order in the asymptotic expansion. And I need to define some of these things for you now. So sigma of theta is basically the drift. So it's u sine theta divided by dyy of theta, where dyy is the 2 component of my d tensor here. So that's a function of theta as well. Now I need to, I'm going to give you an equation for capital P. So capital P actually satisfies a very nice PDE. It satisfies a kind of 1 plus 1 dimensional PDE because the y dependence now has been completely separated out into this exponential, which actually kind of creates boundary layers against the walls, as we'll see in a second. But basically, we've reduced the whole thing down to a 1 plus 1 dimensional PDE, where now I have to tell you what mu is. Mu is very important. It's a kind of effective drift. It's not actually directly the drift that we started out with. It's a kind of effective drift that contains information about the shape of the channel and of the swimmer. So it has a rather complicated expression, but I'll go ahead and write it out anyways because you'll see that there's information encoded in this. So it's sigma over 2 sinh of a function called capital delta, and then e to the capital delta zeta plus prime minus prime. Whereas zeta plus and zeta minus, if you'll remember, are the two functions that are giving me the shape of my wall. So this contains wall information, but then this function capital delta of theta also contains information about the wall. It's 1/2 sigma of theta, and then it's zeta plus minus zeta minus. So this is like the width of the channel. This difference is like the width at any given theta, but it's weighted by this drift. Don't ask me what the intuition is for these kinds of functions. It's a little bit complicated. But what's very nice about it is that these are all just functions of one variable, right? And then you have to solve this PDE, which is 1 plus 1 dimension. So in other words, you've you've put everything into this rather ugly drift, but that ugly drift just encodes the shape of the swimmer and of the domain in it. By the way, you could allow for a deformable body. You could allow for a swimmer that can actually change its shape by having these zeta functions actually be functions of time as well. In other words, if the swimmer changes its shape, that means that this wall distance function now is actually a function of the shape of the swimmer at any given time. And so therefore you can make these time-dependent drifts to allow for a deformable swimmer like paramecium, which swims by deforming its shape, or flagellum, which swims by agitating. So the theory is actually quite general in what you can do with these kinds of equations. Okay, questions so far? You guys are all very silent, but it's only to be expected. Okay, so what can we do with such an equation? Oh, no. Alex, you keep blinking in and out. Okay. What can we do with this equation? Well, one thing we can do, so this is where we're going to start doing some applications in some sense, right? Because now I have a nice equation, and I would like to solve it to learn something about the behavior of the swimmer. So, for instance, the most natural thing to do when you're given an equation like this is to find the invariant density of the microswimmers. Because now the channel is a confined environment, so it can achieve an invariant density with finite normalization. And so you look for the invariant density, which will just solve this equation, but without the dt, of course. Minus d theta p. By the way, in case you're wondering, the reason why there's not a d theta here, capital D theta, is because I redefined time. So I've got a dimensionless time going, and that's why I've got a no constant in front of here. So I've just normalized the way the time. So the invariant density satisfies this. It's actually an ODE, right? But then let's see what happens if I integrate it once. If I integrate it once, I get this, and I'm going to write the right-hand side as omega over 2 pi, where omega is a constant, right? It's an integration constant. But it has a really interesting physical interpretation. There's a nice hint in that if the swimmer is left-right symmetric, if the swimmer has this left-right axis of symmetry, then the constant omega can be shown to vanish identically. It's not an if and only if. There are other cases where the constant omega could vanish, but in particular, if the swimmer has this axis of symmetry, then one can easily show that the constant omega has to vanish. Now, what does that mean? Well, when omega equals 0, this kind of ODE is said to satisfy detailed balance. Right? This is what it's called in the physics literature and some of the probability literature. It's a system basically where the probability flux is actually a constant everywhere. What is happening is that if the swimmer is left-right symmetric, there is no net rotation to the swimmer over time. It bounces up and down the wall, but its average rotation is 0. But if the swimmer is not left-right symmetric, then there can be a net rotation over time. In other words, the swimmer swims and sometimes hits the bottom wall, sometimes hits the top wall, but it can do so in a sort of biased way that over time it will actually precess. And we can solve for the value of this integration constant omega given the shape of the swimmer. So it's already one very interesting piece of information is that the actually we can write even I think I can write a formula which is that omega is equal to the expected value of mu, I think. Yeah. There's a nice formula you can write that omega is the expected value of mu, where expected value is taking over the invariant distribution itself, right? So this is given the invariant distribution. In other words, once you solve for p self-consistently, you can say that the rate of rotation is the expected value of this drift, because this drift is basically an angular drift, right? It's in the theta direction. So if it has a non-zero mean, it means that your swimmer is traversing the domain from minus pi to pi, and therefore picking up a net rotation over time. So, but most of the swimmers that we deal with are left-right symmetric. So we're going to, typically I'll refer to a left-right symmetric swimmer. Like the ellipse that I presented earlier is left-right symmetric. Let me just comment a bit more on what kind of solutions you get for this problem. You can actually solve this ODE exactly for many cases, and you find that the shape of the invariant distribution, so let me draw my wall again. Sorry, I didn't leave myself enough room there. So this is what my domain looks like. And what you find if you find the exact solution to this, or if you do numerical simulations for more complicated wall shapes, is that you find that the swimmers accumulate in places like this, where this is theta equals 0 here. This is 0, and this is minus pi, and this is pi. In other words, there's peaks in the distribution near 0 and near pi. What that corresponds to is the fact that if you have a swimmer with a constant swimming velocity like this, I showed you earlier from the picture that if it arrives near a wall, it tends to rotate and align with the wall. And it turns out that it stays there quite a long time. In other words, the swimmer spends a lot of its time either glued to the top or to the bottom wall. It spends a lot of its time just glued to one wall or the other, and it's only when there's a large enough fluctuation in its angle that it manages to swim and change wall for a while, but then it'll get stuck on the other wall. So this is why the invariant distribution for this, invariant measure for the concentration of swimmers tends to be localized near the walls, which again is something that's observed in experiment. But what's nice about this description is we can see exactly how the shape influences this. In particular, this is where I can tell you now about the different type of ellipse. So if I had an ellipsoid that was swimming like this, in other words, where the semi-major axis was actually perpendicular to the direction of swimming, then if you think about it, if this swimmer comes near a wall, it will tend to rotate into the wall. Not like this one, which becomes parallel to the wall. This one tends to rotate and become perpendicular to the wall. Because of, it hits the wall with its bottom first, and the kind of torque almost causes it to rotate. But this is captured exactly by the modification that this gives to the function mu of theta. And indeed, if you change the relationship between the semi-major radius and semi-minor radius, if you flip them around, you see exactly this transition where the invariant measure is concentrated to pi over 2 instead of 0 and pi. So here the invariant measure is concentrated at near plus or minus pi over 2, which corresponds to the swimmer being stuck with its head to the wall rather than swimming parallel to the wall. And we'll see in a second that this has a big impact on the transport properties of this system. Okay.
Jean-Luc, just one question. So
yeah.
This invariant measure, can I think of this as showing up in the limit as epsilon goes to 0 of the problem?
No. It's true for epsilon is small, but it shows up as t goes to infinity for any epsilon.
Okay.
Yeah.
And that's the time that goes to infinity is the rescale time, or which it's tau, I guess. Tau going to infinity.
Yeah, it's this capital T. That's right. Yeah, the invariant measure is that's right. It'll be the time asymptotic limit of this process. I'm not telling you anything about how long it takes to relax to that measure, right? That's an interesting question in itself, and probably one can do something since this system is a 1 + 1 dimensional system, but I don't actually know how to estimate this relaxation time. It's actually a very interesting question it's a mixing question basically, right? We want to estimate the relaxation time for this distribution, which is not the constant distribution, unlike incompressible flow, right? So we would like to compute, one interesting thing to do would be to compute at what rate is this measure approached. Yeah. Thanks, Theo. Okay. Right. So So we have our invariant measure P. invariant distribution for this microswimmer in the channel, this is what I call the reduced invariant distribution, in the sense that it's in this description where d theta is small, then we have this thing. Of course, it's really a function of y and theta, but capital P is the theta part. It's the marginal distribution, right? So it's the marginal P of theta, right? The y dependence is that e to the sigma y that we had earlier. Okay, so now I want to ask another question you can ask about a system like this. Once you have this stochastic description, you can ask another question about the so-called reversal time of this microswimmer. So what is the mean reversal time? So the mean reversal time is the expected time it takes for the swimmer to start from theta equals 0 and end up at theta equals pi. So in other words, initially, say the swimmer is swimming in this direction, and then after some time, it just happens to now be swimming in the pi direction, and there's going to be some expected time after which that'll happen, right? And it turns out that's a mean exit time problem, because you can think of theta equals 0 and theta equals pi. You can think of theta equals 0 as your initial condition, and you're trying to find the first passage time, or the mean exit time, or the hitting time, to theta equals pi. And that has a nice equation. Now that we have this PDE formulation, we can write down a PDE for this mean exit time as well. And it's just mu tau prime plus tau double prime is equal to -1. Where mu is our drift, our drift, which is a function of theta only from the previous slide. Here again, the units are expressed in units of 1 over d theta, so there's no diffusion that appears. You might have seen this particular form, right? The Laplacian is equal to -1 is the mean exit time equation in the absence of drift, but this is the mean exit time equation in the presence of with a drift, and you have to add boundary conditions to this, and for our purposes, we're going to say that plus or minus pi are like absorbing points, right? If you hit them, the probability goes to 0, therefore they are exits for our problem. We want to know the first passage time to tau equals 0, to theta equals 0, and then the mean reversal time, so if we call this, is going to be the solution of this evaluated at 0, right? In other words, the solution to this problem is tau of theta, which tells you the expected time to reach theta equals plus or minus pi, starting from initial condition theta. But if you value theta equals 0, that's exactly the reversal time, starting from 0 when you hit pi. And this has been considered before in a related problem by Holzmann and Schuss. 2014. They have a review paper called the narrow exit problem, where they consider all these types of so-called narrow exit problems, where you can calculate the mean exit time asymptotically, but they are considering it for diffusion only. And for a so-called a needle, in other words, not an ellipse, but the limit of an ellipse as one of the axes goes to 0. So for b equals 0, if you will, where remember that a and b are my semi-major and semi-minor axes. And we'll see that the answer changes radically when you add swimming, of course. But their approach is completely different, and their approach is valid for any d theta, but a small exit. I'll describe what that is in a second, whereas our approach is valid for small d theta, but any size exit. So both of our limits are a little bit different, but this leads to an extraordinarily nice form for this mean exit time. If you solve this and you assume that the swimmer is left-right symmetric, so only in the left-right symmetric limit does this formula hold. It says that the mean reversal time is the integral from 0 to pi of d theta over p of theta. Again, this is only valid when evaluated at 0, and it's only valid for a left-right symmetric swimmer, but it has this extraordinarily simple form. It basically, you just find your invariant density from the previous example, and you integrate 1 over the invariant density over your domain. Because you can this is symmetric now, so you could go from minus pi to pi, it's the same thing. And if p theta vanishes anywhere, then the reversal time becomes infinite, because that means that you're cut off from the exit, right? You're not able to reverse directions. So the reversal time goes to infinity if p of theta vanishes anywhere. But this also shows you that the reversal time is dominated by the smallest values of the probability. In other words, there are bottlenecks in the reversal process, and it's wherever you're least likely to end up that dominates how long the reversal time ends up taking. So for example, so let me just write that down. The integral is dominated by bottlenecks. Which are the small p of theta. And in fact, you can use this to estimate the reversal time for some simple swimmers. This integral, in other words, once you find the invariant distribution, you want to carry out this integral, you can approximate the integral by expanding near the minima of p. And then this gives a rather accurate expression for the reversal time. And you find the following. Let me give you an example in the case of the needle. So the needle, again, is a segment of length 2a. So it's like an ellipse with b equals 0. It's the limit of a infinitely thin ellipse. It's actually still a pretty good model of a swimmer because there's lots of swimming organisms that are very long and skinny like this, like there's rod-like bacteria. And so for the needle, let me define a Pecklin number. My Pecklin number is going to be defined, it's called beta, is going to be ua over 2 dy. And I'm going to assume that it's big. It doesn't have to be very big. When I say big, it can be 2. And the asymptotics work pretty well. It turns out that if in the case of this needle, you can estimate this reversal time, tau of 0, by computing its invariant density and then approximating the minima of the invariant density appropriately. You find a very pleasant formula for tau of 0 as an exponential of the Pecklin number. E to the beta over beta, this is actually in the limit where dy is equal to dx. I have an expression when dy is not equal to dx as well, but it's just more complicated and it illustrates the point to pick dy equals to dx. So this expression is where it's radically different from the diffusive scale that was found by Holzmann and Schuss, which I'm not going to write down for lack of time. Their diffusion time was something like 1 over d theta, whereas this is much, much longer because it's an exponential of this Pecklin number. And again, this is due to this sticking process. It's because the swimmer ends up being parallel to the wall, and then it just gets stuck there for very long times. And eventually, once in a while, it gets lucky enough to get a fluctuation that forces it to reverse direction, right? But it happens very seldom, and it happens exponentially rarely in some sense. Okay, right. And you can compute a similar expression also for if the needle is swimming in the other direction, right, the perpendicular direction, and you get just a different reversal time. In other words, if the swimmer is such that it likes to stick its head at the wall rather than swim parallel to the wall, then you get a different expression for the reversal time. So again, the shape is captured in this derivation, especially through this function mu, right? Mu is really where the shape completely gets encoded. Okay. Questions so far? I only have a little bit more to say. Unfortunately, I had homogenization in my title. I'm not going to get much of a chance to talk about homogenization. I will give you the punchline rather quickly in a few minutes. What I want to do next is basically, you might be wondering why I'm computing this reversal time. I compute this reversal time because I cared a lot about transport. And so now we can ask the question, if I release a bunch of these microswimmers in a channel, and the channel could be a pipette or something like this, right? They're going to start swimming along the channel, and then once in a while they're going to reverse direction. And so the rate of spreading, so the effective diffusivity of this collection of swimmer, is an interesting quantity to compute, right? I would like to know that if I have a suspension of millions of these swimmers and I let them go in a channel, they will slowly spread as they reverse direction over time. And what is the effective diffusion constant for this process? When we first started this, we suspected that actually we might be able to relate it to the reversal time in some way. Because if you think about it, the reversal time is exactly this, right? Every time you're not reversing, you're going at velocity capital U, and then once in a while you reverse, and then you go by capital U another way, and it's the mean reversal time that tells you the length of these excursions each time. So we would expect, just intuitively, that the mean reversal time is related to the effective diffusivity, or vice versa. And it took us a long time to figure this out. So again, let me just draw a picture here. We would like to compute the effective diffusivity now of a swimmer which is in a channel but which reverses direction over and over again. So we want to know the expected value of its squared displacement in x. And we define the effective diffusivity as being the linear growth of this expected value in the limit as t goes to infinity. I'm not going to write the limit as t goes to infinity, but it's an asymptotic result. And again, because of lack of time, I'm not going to do the homogenization calculation here, but it turns out that you can homogenize the Fokker-Planck equation from a previous slide in the x direction only. In other words, it's still confined in the y direction and it's still confined in the theta direction, but in the x direction, you can do a multiple scale expansion where you think of a large scale in x and a smaller scale in x, and you find eventually that you get an enhanced diffusivity. I'm not going to write the formula, there's a cell problem, but here's the interesting thing. There's a beautiful bound for the effective diffusivity, that the effective diffusivity is bounded below by 1/2 tau of 0 and u squared, which is exactly the intuitive notion that I was just presenting, that you take steps of size ut0, right? In the sense that that's how far you go, and you go each in direction. So this is the leading order estimate, if you will, for the effective diffusivity. It's how often you reverse direction multiplied by u, which tells you by how far you travel, and then normalized by another u because it's the squared displacement that you're interested in. So in other words, maybe you can see it like this. You can write this as u tau squared over tau, right? So u tau is the typical displacement that you get between reversal times tau, and then the time at which this is happening is every tau. So the net effective diffusivity is equal to this. But what's nice is that this is actually a rigorous bound, in the sense that this is the best you can do. Anything else will mess up the effective diffusivity. I should point out that this bound is actually only good for dx bigger than 2 dy, or to dy over 2. I don't have any good intuition as to why that is. We check numerically, and it's actually true that the bound fails if you let dx be smaller. And I don't have any good intuition as to why that limit should be different. So I don't know yet. So that's about all I have to say. Hongfei and I are finishing a preprint on this. If you're interested, we'll have it ready probably in a few weeks. Okay. Thank you very much.
Jean-Luc, could you just explain why the expected displacement square should grow linearly with time at long time?
Oh, yeah. So you have to rescale time and space appropriately, right? In the sense that you rescale space by a small number, eta, which is the length, the length scale rescaling, and then you rescale time by eta squared, right? So that the diffusion and the displacement match up. And then I guess, intuitively to me, I think of it as, because it's undergoing a random walk, right? The mean displacement of the swimmer is actually 0, and so therefore it gets these large displacements each time and then reverses and then comes out each direction, and the limiting process is basically like Brownian motion if you rescale things out far enough and if you rescale time appropriately. This comes out of the homogenization calculation basically after doing this rescaling, but I think the intuition is just that it's a process with mean 0 and bounded steps, if you will, and therefore it has to converge to a Gaussian process if you rescale things appropriately and you wait long enough. If you look at large enough scales and long enough times.
So if you had a very narrow channel where the particle could never turn around.
That's a good question.
Then it would be more like ballistic, right?
Yes, absolutely. So I forgot to say that, in fact, when I was drawing my channels earlier. So I drew these channels like this, right? But there will come a point where they will overlap, right? Where this configuration space that this is probably too small. Let me draw a bigger picture. I was drawing the two wall functions for my two sides of my channel, but there will come a point where they will overlap if I make the channel too small. And so that's when the width of the channel is less than the width of the swimmer. In that case, the swimmer is forced to swim in a single direction. So from our perspective, what that means is that now the configuration space is actually disconnected. It's now made up of two connected components, and you can find the invariant distribution on each component separately, and what that means is that it depends on the initial condition now. It's no longer ergodic, right? If I place a swimmer moving one direction, it stays moving one direction. In that case, you're right. There's an expected value. The expected value of x is not 0 anymore, and so you get ballistic motion at leading order. And then probably this calculation will actually give you the effective diffusivity around that. Sorry?
Do you think you could do some asymptotics where you transition between the sort of fat channel to the thin channel?
Oh, absolutely. Yeah. In fact, Holzmann and Schuss, the paper that I mentioned earlier, they work in the limit where this gap is very small. So they call this the narrow exit problem, right? So when you have a very small gap here, you can exploit that because your entire process now is dominated by how long it takes you to transition through this little region. That's true in their case because they don't have drift. For us, that's not true because our process is determined by the sticking to the wall, if you will. In the case without swimming, the swimmers don't spend any particular amount of time near the walls. But if you add swimming, they tend to get glued to the wall, and that's what dominates everything. Whereas for them, what makes the reversal time being very long is the fact that they're working in the limit where the swimmer has almost exactly the same width as the channel. And so it takes it a long time to find a way to reverse. It's like getting your couch through a staircase, right? It's just, you have to jiggle it exactly the right way to be able to get it up in your apartment. Right.
Thank you.
Thank you, guys. Any other questions?
Okay, if there are no other questions, thank you very much again, and thanks for being our first.
Yeah, it was fun.